Good morning, everyone. Welcome back. Let's continue along with our comparison tests. We ended last time with the direct comparison test, and we did a non-example, meaning we had a series 1 over n plus 1 here. We showed that it was smaller than 1 over n, so we were able to compare it to a series that looked like it should be compared to. Yeah, 1 over n plus 1 sure looks a lot like 1 over n. But unfortunately, when you have a series smaller than a divergent series, the comparison test doesn't tell you anything. Yeah, sure, your series is less than infinity. That's not very useful information. It's not conclusive. So what the limit comparison test does, which we're going to write down soon, is it says, how can I formalize the statement that 1 over n plus 1 sure looks a lot like 1 over n. And what we're going to say is basically the limit of these two, specifically the ratio of these two, eventually these are the same series. So they must both diverge together or they must both converge together. So why don't we just notice that if we take the limit as n goes to infinity, and I'm going to put 1 over n plus 1 on the top and 1 over n on the bottom. Now, if this ratio, without the limit there, hide the limit, without the limit, if you take a fraction of two numbers and it's equal to 1, that means they're exactly the same. Right? If you take two numbers and the ratio is 5, it means one is 5 times bigger than the other one. So what we're going to say is, look, eventually these two series are basically the same, or they're a multiple of each other. And a multiple of a finite number is a finite number, and a multiple of a non-finite number is a non-finite number. But let's look at this limit. I'm going to rearrange this. This is n over n plus 1. Which we know is 1 over 1, because n and n plus 1 both have the same degree. You take the quotient of the leading coefficients if the degrees are equal. And that's equal to 1. So eventually, aka at infinity, 1 over n and 1 over n plus 1 are the exact same function. Eventually, the fraction of the two is equal to 1. They're the same. That means that they should both diverge together, or both converge. Now I know that this series 1 over n diverges, so this series 1 over n plus 1 should too. And intuitively you knew this. You looked at the series 1 over n plus 1 and you immediately knew. That looks a lot like 1 over n. It's just off by a little bit. It should also diverge. And this limit here is formalizing that, saying, yes, eventually these two are the same series. And because one of them diverges, the other one has to, because they're basically the same. So let's write this down. Generally, this is called the limit comparison test. So remember, I'm testing a series an using bn. So I'm testing one series using another one. So the an I'm given, the bn you need to come up with. In the previous example, it was the an was 1 over n plus 1. The one I came up with was 1 over n. All right? Now, if I take the limit of the terms, like I did above, and that's equal to a number between 0 and infinity. So what I'm saying is, in the previous example, c was 1. The limit was 1, which means they're exactly the same. If the limit of this is 2, it means one is twice as big as the other one. And if one converges and one's twice as big, it's just twice as big. It also converges. So if the limit of these is a constant, then either both an and bn converge or they both diverge. This is very integral test flavored. They converge together or they diverge together because they're basically the same series, maybe just a multiple of the other one. All right, let's look at some examples of this, and you'll see why. Well, you've already seen why this is such a useful theorem, because up here the comparison test was non-conclusive. But the limit comparison test, I took the limit of the terms and got 1. Since the limit was 1, I'm saying these are essentially the same. So since this one diverges and this one is essentially the same as that one, it has to diverge too. So let's look at another divergent series here using the limit comparison test. Example. So, actually, I'll just leave off the bounds. The bounds are implicit. N squared minus 5n over n cubed plus n plus 1. So this is where you get a little complicated, because this, you can figure it out for yourself. This is going to look a lot like a harmonic series. So I'm going to compare this with 1 over n. And I knew that because the top of this series is n squared, the bottom is n cubed, n squared over n cubed is 1 over n. You have to be a little clever when you're choosing your series to compare here. Now I can't directly compare these two and use the direct comparison test, because the an in this case, n squared minus 5n over n cubed plus n plus 1, is actually going to be smaller than 1 over n, and you're in the same situation as you were with the first example. Now, let's use the limit comparison test. So I'll take the limit of these two series, the terms of these two series, and see what happens to them. Well, I get n goes to infinity of n squared minus 5n over n cubed plus n plus 1, all divided by 1 over n. Now you have to be a little careful with your fractions, but this simplifies nicely because I just flip that fraction around, it goes on the top. And you might be able to see where this is going, because now on the top I've got a cubic. I've got n cubed minus 5n squared. So this fraction is a cubic divided by a cubic. Same degree. So the limit of this is just the quotient of the leading coefficients, both 1 in this case. So this is equal to 1. Wonderful. And since 1 over n diverges, and because 1 is between 0 and infinity, my other series also diverges by the limit comparison test. Beautiful. All right, let's look at one more. One more before we tidy up here. So let's look at, first I'm just going to pop a page in there. Might as well start on a new page. Example. Right, let's look at this series. 1 plus 4 to the n over 1 plus 3 to the n. All right, we're going to compare this. This looks like the geometric series. And sometimes you don't choose the right comparison the first time. Sometimes you have to do it once or twice. But to me, this looks a lot like this series. You basically strip all of the constant terms and you strip all of the lower power terms. You go to the biggest things and take those. The biggest thing on the top of this one is 4 to the n, and the biggest thing on the bottom is 3 to the n. So I'll try it out. So let's take the limit of this. So an, the thing I'm testing, is 1 over 4 to the n over 1 plus 3 to the n. And the thing I'm going to compare it to is 4 to the n divided by 3 to the n. Play a little bit of fraction gymnastics here and flip that 3 to the n over. Kind of play a little more fraction gymnastics, so I guess this one's more just multiplication, but I'm going to just group these things around, and then we got 1 plus 4 to the n over 4 to the n. Good. And this, so that first piece, so actually you can even break this up further if you don't want to skip a step. You can do this as long as one of the factors doesn't go to 0 or infinity. Then you'd have to use L'Hopital's rule, which thankfully we're not going to have to do here. But just breaking this up, this is equal to 1 over 1, because the top part has a 3 to the n and the bottom part has a 3 to the n. And there's only one 3 to the n on the top and one 3 to the n on the bottom, times, over here, it's also 1 over 1, because there's one 4 to the n on the top and one 4 to the n on the bottom. And that's equal to 1, which is bigger than 0. All right, so 1, the limit, as n goes to infinity, an over bn is equal to 1. 1 is between 0 and infinity. This series, 4/3 to the n, that's the 4 to the n over 3 to the n, diverges, since it is a geometric series, with r equals 4/3, which is bigger than or equal to 1. So I've just compared my series to a divergent geometric series. And eventually, the two series are the same. That's what it means for the limit to be 1, the limit of the ratio to be 1. Eventually, 1 plus 4 to the n over 1 plus 3 to the n is approximately the same as 4 to the n over 3 to the n. And since 4 to the n over 3 to the n diverges, mine has to diverge too, by the limit comparison test. So, by limit comparison test, this series also diverges.